Hi, my name is Daniel Casey, and today we're going to be looking at some of the basics of flood frequency analysis. This will be in two parts. The first will be an introduction of some of the basic statistics, and the second part will be looking at an example of carrying out a flood frequency analysis. So the first thing we'll be looking at is some of the basic statistics. Let's assume that we have many discharges. In this case, we have a sample of 10,000 discharges ranging from something lower than 10 cubic meters per second to something greater than 40 cubic meters per second. We can see from this histogram that some of the values occur more often than others. We can calculate a mean value out of this as well. So the mean for these samples would be 25. And here on the y-axis, we have the plot of the number of events. So the highest values in terms of occurrence would be around 800 over the 10,000 samples, for instance. But one thing that we can do from this sample is we can divide the number of events over the total number of events, which is 10,000, and get what we would call a frequency of events. And this is exactly what we've done here. We basically divided the 800 by 10,000, and this gives us a frequency of events, which will denote the probability density function, small f of x. And one important characteristic of this probability density function is that the summation of the gray area underneath the curve here is equal to 1. Same values of discharge, but expressed in terms of frequency. Now, we can look at some of the parameters of some of these frequencies. For instance, we can look at the central tendency. An example of this would be the mean, the median, where the median would be representing the value of the discharge, where there's 50% of the area underneath and 50% of the area above. We can also identify the mode, which would be the value with the highest frequency. But we can also look at other parameters such as dispersion, the variance, standard deviation, and the range of the data. Here we have two examples where the mean is the same at 25 cubic meters per second, for instance, in terms of a discharge, where the variance or the standard deviation or the dispersion would be different, here having a greater dispersion. Now in hydrology, we're not really looking at the probability density function, but we're looking mostly at the cumulative density function, which we will denote this as large f of x. The cumulative density function is the area under the curve of the probability density function from minus infinity to a value of discharge. Let's say here we would say that it's x1. So if we look at the representation before, it would be this area underneath the curve, and this would be x1. Then the cumulative distribution becomes the probability of an event being lower or equal than the discharge x1 would be the cumulative probability function. Now related to these large f of x, which is the cumulative density function, which we have here, is the recurrence interval. And the recurrence interval equation is given by this equation here. The recurrence interval represents a mean period in years separating certain hydrological events. For instance, if we have a 20-year recurrence interval, i.e. a t equals 20 years, then in over 100 years of information, this event of this magnitude in terms of discharge should occur on average 5 times. Similarly, if we have 200 years of data, then we should see 10 of these events of that magnitude or greater over a 200-year event, or over a 200-year period, excuse me. So this means that it's not a matter of occurring at a specific time, it's just that during a sample time of 200 years, you would most likely see 10 times the 20-year discharge. So this is how we define recurrence interval in hydrology. Now, when we want to carry out a flood frequency analysis, we generally look at recurrence interval of different magnitude, the 2-year event up to the 100-year event. But in order to do that, we need to fit the annual maximum discharge to a distribution function. And the annual maximum discharge can be used, we can use instantaneous data or we can use daily data. And in this particular case, we'll describe the case for daily discharge. The different distribution that can be used to do this, the flood frequency analysis, would be such as log normal distribution, Gumbel distribution, generalized extreme value distribution, and many more. Certain conditions need to be applied, or we need to satisfy certain conditions in order to carry out a flood frequency analysis. And these would be independence, so there's no autocorrelation within the data. But this, if we look at the annual daily discharge, it's generally one which is very often satisfied, because you would not believe that the daily maximum discharge of 1 year would be influenced by the daily discharge maximum of the previous year, for instance. We need stationarity within the time series, no trends within your data, and the data needs to be homogeneous. Data comes from a single population. For instance, if you had flood value downstream of a reservoir and you would turn this river into a natural, then your population may not be homogeneous. But under natural condition, very often these homogeneity is satisfied. So thanks for watching, and see you in the next presentation.